All right, so welcome back. I think we're on lecture 4 at this point. And today we're going to talk about the mean value property and the maximum principle. And the mean value property we're just going to use to prove the maximum principle immediately. I'm not sure if the mean value property gets used anywhere else in Gamlen's book, but the maximum principle will be used over and over again. So this is a good thing for us to know. And then next week, we're going to finally start with the fancy integration theorems that everybody loves after complex analysis. Okay, so let me pull up this guy. Okay, so let's start by defining a function, h from a domain to the real numbers. So this domain sits in the complex numbers here. And let's let it be continuous on all of D. And also let Z0 be an element of D. And suppose that D contains the disk centered at Z0 with radius R. And we're talking about the open disk here. Okay, so I'm going to state this as a definition, but this definition should be justified by your intuition, and I'll explain in a second. The average value of this function on z minus z0 equals r, so this is a circle, is just the integral from 0 to 2 pi of h d0 plus r e to the I theta d theta over 2 pi. So all of these points are just points that live on the circle defined by this equation here. And as we integrate theta from 0 to 2 pi, we're just going all the way around the circle. So we're integrating this function over the entire circle. So this is like a parameterization of a line integral. Okay, so why do we call this the average value? Well, this d theta over 2 pi is a probability measure, right? If we integrate without this h here, we get 1. And so when we weight it by this h guy, what are we doing? Well, we're taking like an expected value of h, right? And so that is kind of justification for calling this an average value. Okay, so since h is continuous, the average value, which we're calling A of R, it varies continuously as well. And that's with the radius. Okay, now since the values of h, maybe I should write this, since the values of h of z are all near h of z0 when z is near z0. So that's what continuity means. The averages are also near h of z0. That's when R is small, right? Because when R is small, what's happening in here? Well, these z0 plus r e to the I thetas are all near z0, right? And we know h is continuous, and so the value of h with this guy plugged in should be near h of z0, right? This is just what it means to be continuous. But we can kind of formalize this point. We can take the difference between the area and h of z0 in magnitude. And well, this is the magnitude of the integral from 0 to 2 pi of h of z0 plus r e to the I theta minus h of z0 d theta over 2 pi. So this guy is a constant, so I can write it as the integral from 0 to 2 pi d theta over 2 pi, right, of this guy. And that's how I move it in here. But this is less than or equal to the integral from 0 to 2 pi of the magnitude of the integrand. Right? We think of the integrand as a sum. In fact, it's defined as the limit of a sum. And so if I sum, well, this is sort of like a triangle inequality, right? If I sum the, what am I trying to say? Positive, if I sum the absolute value of something, it's going to be greater than summing the signed version of that thing and then taking the absolute value at the end, right? Because those in between terms can take away some of the magnitude if they're negative. Okay, so since h is continuous, we are guaranteed that the integrand approaches 0 uniformly in theta. So why? Well, remember when we're talking about continuity, how is it defined? It's defined in terms of limits, right? And what do we mean by a limit in the complex plane? We mean that the limit exists whenever you can go from, say you're going to this point, whenever you can go from any old direction, and that limit along that curve heading to that point exists and is the same for any particular direction you use, right? So the idea is that if you have continuity, well, since the continuity is defined in terms of limits, well, it shouldn't depend on this angle theta at all, right? And so this guy should go to 0 uniformly as r approaches 0, uniformly in theta. Okay. And so as a result, what we have is that, so if this guy goes to 0, this is less than or equal to that, and it's positive. So we have this guy must go to 0 as r goes to 0. Okay. So in other words, as r approaches 0, this a of r guy approaches the value of h at the center of this disk. Okay. So that kind of motivates the next theorem that we're going to go ahead and prove, which is the mean value property. So it tells us that if u is a harmonic function on a domain D, and if the disk, so this is the open disk, is contained in D, then in fact, u of z0, the value at the center of the disk, is equivalent to the average value of u. Okay, so before we argued that the value of this guy would approach the value of the function at the center of the disk as r approached 0. And now we're trying to say that, in fact, all along this disk, uh, 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 the value of this integral is, in fact, the value of the function at the center. And this is when u is a harmonic function. Okay, proof. So first, from Green's theorem, so remember what Green's theorem said. It told us that the integral along the boundary of some domain of this differential is equivalent to the integral over the disk. Put two integrals there of this difference of partial derivatives. Okay. So from Green's theorem, we have that the integral along the circle here. So you'll see this notation sometimes for line integrals over closed curves. People put this little circle along the integral so you know it's a closed curve. It's clear when you put this circle down here, but doesn't hurt to be redundant. So this tells us that, well, this guy, Green's theorem will tell us that this guy is equivalent to the integral over d, so the disk, maybe I shouldn't call it d. I'll just write disk. Okay, so the disk meaning the disk contained inside this circle. So this double integral here, this guy is equal to this double integral over dq dx. Q here is this guy, du dx2, forget about that, minus dp dy. That is, so p is minus du dy, so we get another minus sign here, d2 u dy2 dx dy. But we're assuming that u is harmonic, and so this guy is 0. And so this whole thing is 0. Okay. So this equality is Green's theorem. This equality is the assumption that u is harmonic. Well, on the other hand, we can parameterize this guy. And the way we'll do it is we'll define, well, we're gonna switch to polar coordinates. Polar coordinates centered at x0, xy. Well, then this tells us that 0 is equal to, and then we can rewrite this integral as r, the integral from 0 to 2 pi du dx cosine theta plus du dy sine theta d theta. So let me unpack that. This dy becomes right here. This dy becomes r cosine theta, and then this dx becomes minus r sine theta. And we have a minus sign here, so they cancel. Okay, but remember that du dr is the same as du dx dx dr plus du dy dy dr, which is again, well, it's this guy. And so what we have is that 0 is r integral from 0 to 2 pi r du dr. and well, we're evaluating this guy. Where are we evaluating it? We're evaluating it at this point. So maybe I'll sneak that back in here. Okay, now let's go ahead and divide by r. Let's throw that guy away, and then we'll also divide by 2 pi to put the 2 pi over here. So we have that 0 is, oops, I have an extra r. We don't need that. So we have that integral from 0 to 2 pi du by dr evaluated at z0 plus r e I theta d theta over 2 pi. This guy is equal to 0. And since u is smooth, well, smooth enough, right? We can pull this derivative out. And so this tells us that the value of this integral, which is the thing we're concerned with over here, is in fact constant on, this implies that the integral is constant on 0 less than r less than rho. Okay. So on our disk, essentially. So since u is continuous at z0 by assumption, well, the average value tends to u of z0 as r goes to 0. This is the thing we showed before I even stated the theorem. Right? But if it approaches u of z0 and is constant, well, then it must be equal to u of z0. So we have u of z0 equals integral from 0 to 2 pi u of z0 plus r e to the I theta d theta over 2 pi. That completes the proof. Okay, so if you have a function u and it's harmonic on a domain, and that domain contains some disk, right? And you take the average around that disk, it turns out that that average is equivalent to the value of the function at the center of the disk, regardless of what you choose for that radius r. Okay. Okay. So this is a nice property to have. So we give it a name, right? We say a continuous function h on a domain D has the mean value property. If for all z0 in the domain, we have that h of z0 is the average value. I should say centered. Okay, so let me just state that precisely. So what I mean is for all z0 and d, there's an epsilon such that h of z0 is the integral from 0 to 2 pi h of z0 plus r e to the I theta d theta over 2 pi. This is the average value for all r between 0 and epsilon. Okay. So we learned from the theorem that harmonic functions have this mean value property. Great. Maybe I should say harmonic functions with the additional assumption of continuity. Okay. So now what we're going to do is we're going to use that mean value property of harmonic functions to go ahead and prove something called the maximum principle. And we're going to restrict our attention to the real version first, and then we'll move on to the complex version, because we're going to use the real version to prove the complex version. This is the strict maximum principle. And I'll just specify this is the real version. Okay, so let U be a real valued harmonic function on a domain D such that U of Z is less than or equal to M. We can write this because U is real valued for all Z and D. If U of Z0 achieves this maximum for some Z0 and D, then in fact U of Z is constant on D. Okay. So if you're a real valued harmonic function and you're bounded above by some constant, and you also achieve that constant somewhere on the disk, then in fact you're constant, or sorry, somewhere in the domain, then in fact you're constant on that entire domain. Okay, let's go ahead and prove this. So the path forward here is we're going to use the mean value property to show that the set of points where U achieves its maximum is in fact an open set. And then we're going to note that the complement of that is also open. And so we have the union of disjoint sets being equal to our domain. And since domains are connected, that's going to imply that one of these two open sets is actually the entire domain. Okay, so suppose U of Z1 is equal to M. Well, then we can write, well, we have 0 is equal to the integral from 0 to 2 pi of U of Z1 minus U of Z1 plus R e to the I theta d theta over 2 pi for 0, or sorry, R between 0 and rho. So this is the mean value property that we just proved. So since U of Z1 minus U of Z1 plus R e to the I theta is greater than or equal to 0. So why is that the case? Well, this U of Z1 is defined to be the maximum of U on our domain, right? And this circle is contained in our domain. So this guy must be less than or equal to M. So we must have positivity here. So since this guy is non-negative, I shouldn't have said positivity, I should have said non-negativity. And it's also continuous. Difference of continuous functions is continuous. The integral is 0 only if the integrand 0. And so that tells us that, since it is in fact 0, that tells us that u of z1 plus r e to the I theta must be equal to u of z1, which is in fact equal to that maximum. And this is true regardless of theta, right? This is true for theta between 0 and 2 pi. And it's also true for r between 0 and rho. And so what does this tell us? This tells us that the set of all u of z which achieve the maximum contains an open disk. Open disk centered at Q1. Right, so we've shown here that all the points for which theta is between 0 and 2 pi and r is between 0 and rho are also, the evaluation of the function at those points is also m. So all of these points are also contained in this set, right? These are all the points defining that disk that I'm talking about, right? And so that disk is contained in the set, and that's the definition of a set being open. Right? So that tells us that this set is indeed open. Okay. Now, m is the maximum, so the only other option for the evaluation of the function within this set is that the evaluation is less than m, right? So we have the complement is this set, right? And this is also open. And this is because u is continuous. So the idea is, well, if you pick any point in this set, since u is continuous, those points that are near, so let's call the point z0, right? Those points which are near z0, when you evaluate at those points, they should also be close to u of z0. And so they should also be bounded by this m guy. And so when you take that disk of points small enough around z0, you'll find that disk is indeed contained in this set. So all you have to do is shrink the disk small enough to fit it in this set. Okay, but the point is the continuity guarantees that this set is open. And the union of these two sets is our entire domain, right? And these sets are obviously disjoint. You can't be both equal to m and less than m at the same time, right? But a domain is connected, and so the only way this can be true is if one of these sets is empty and the other one is the entirety of D, right? So this tells us that either u of z is less than m for all z and D, or u of z is equal to m for all z and D. But we already know that by assumption, there's a point which achieves the maximum. And so this must be the case. And so that completes the proof. Okay. So I like that proof. It uses a little bit of point set topology, which is good to see sometimes. Okay. Any questions so far? All right. So we've learned if we have a real valued function with a real valued harmonic function on some domain, which is bounded and achieves that upper bound, then in fact it's constant on the entire domain. It's equal to that upper bound. Okay. So let's move to the complex version. So this is the strict maximum principle again. Let H be a bounded complex valued harmonic function on a domain D. So when we have a complex valued function, remember harmonic here means that the real and imaginary parts are harmonic. If it's bounded by some constant m for all z and d, and the modulus achieves that maximum, so not the function itself, but the modulus for some z0 and d, then in fact h is constant. Okay, here's the proof. So first, what we're going to do is, so notice that we only require h to achieve the maximum. Sorry, we only require the modulus of h to achieve the maximum. Okay. Well, if we replace h of z by lambda h of z for an appropriate lambda with modulus 1, then we can assume that in fact the function achieves that bound. Right. So if the modulus of h achieves the bound m at z0, well then there's some phase that can multiply by that'll bring the function back to, or get rid of the phase of the function, right? So that it achieves this value m. Okay, so let u of z be the real part of this function. Well, by assumption, then u is harmonic, right? That's what it means for h to be harmonic. On D, and it attains the maximum at u0 or at z0, right? And u of z0 is equal to m. Okay, so then by the strict maximum principle, for real valued functions, we have u of z equals m for all z and d. So we've used the real version here. And now since the modulus of h is bounded above by m, and the real part of h is equal to m, well, this guy, remember, is the square root of, the real part squared plus the imaginary part squared. So if the real part is already equal to m, well, then that must mean that the imaginary part must be equal to 0. And so this tells us that h is constant. right? Because the real part is equal to this constant, the imaginary part is 0, and so the whole thing is constant. So that completes the proof. Okay. So there's a corollary of this, which gets referred to not as the strict maximum principle, but just as the maximum principle. I'll just go ahead and write that down. Let h of z be a complex valued harmonic function on a domain D such that h extends continuously to the boundary of D. So this symbol in front of a set just means boundary. If the modulus of h of z is bounded above by m for all z on the boundary, then it's bounded by m for all z and d. Okay. So proof is a few steps. It's so if you have a continuous function on a compact set, it does obtain its maximum modulus. Right? Continuous function on a compact set achieves its maximum. Right? And well, let me write this down. A continuous function on a compact set obtains its maximum modulus. Okay. So this is something from real analysis. Well, except for the modulus part, but the modulus part is just making this a real function, right? And then we're stealing the result from real analysis. So the set we're dealing with is the union of, so our set is the union of the domain with its boundary, and this is closed and bounded, and hence compact. Okay, and so that tells us that H achieves its maximum modulus at some point in D, or rather in this union. If H attains its max modulus at some Z0 in D, then it is constant. That's our maximum modulus principle. And so in all cases, H attains its maximum on the boundary. Okay, so that completes the proof. All right. So again, this maximum modulus principle is the thing that's going to be coming up later, and we'll make use of to prove some nice results from complex analysis. Any questions?
a short one today.